Right, everyone, let's get back to the topics that we're discussing in the last several lectures. So we have a lot of things to cover today, really good things. Now, I want to just make a quick comment that obviously what we have covered in the last probably couple lectures, certainly what we covered in the last lecture, and what we are going to cover today, those are probably the most difficult things that we are going to cover in the whole course. However, you need that knowledge in order to understand pretty much everything else that we're going to do in the rest of the class, right? So you have to get through these lectures, rewatch the videos if you have to, look at the slides online. I'm going to post, I've already posted links to papers and materials. I'm going to try to post over the weekend a link to some notes of my own that you can look at, but make sure that you go over all that information because these are the basics of machine learning pattern recognition that we're going to use during the rest of the course, okay, to define all the cool methods that we're going to define in this class. All right, wonderful, bless you. So let's review very quickly what we had. So we said that we have a set of images or a number of sound signals or DNA vectors, right, of the basis, DNA basis, and so on. Whatever your problem is, or in communications, you have some other type of signals, right? So I'll stick with images of faces. It's the classical example I've been using. So I have an image of a face, or I have n images of faces here, right? And each image has a certain number of pixels. We said this is p pixels, so I have a vector x11. So this is x1 vector represents the first image, and it has x11 through x1p, the p pixels, right? And this is the nth image, xn, xn1 to xnp, okay? That's what we have. And now that means that we are in the real domain of p dimensions. So I'm going to draw 2 dimensions here. And then these faces are represented here. Each xi is represented here as a vector, right? A point, meaning a vector, in my feature space. So this is, of course, my feature space. Right? And then what am I going to do? Well, one thing that we have mentioned is I could compute correlations. The correlations between these dimensions represented by their basis vectors, EI, EJ, right? And one way to compute correlations is by computing the mean. So we have here the mean, mu, and the covariance matrix, sigma x. And the mean, mu, and the covariance matrix represent a normal distribution, right? So my underlying assumption here is my data is drawn, so each xi that I have is drawn from that normal distribution, right? That's my underlying assumption. Remember that I said we're going to talk a lot about probabilistic methods. That's what we mean, that we are assuming that there's an underlying distribution from which our samples are drawn, right? And because this is a parametric distribution, we're going to talk about parametric models, okay? All right. So if this is our assumption, then the best we can ever hope to do under these assumptions, right? So correlations, normal distribution, and so on and so forth, is to use a method that's called PCA. And what does PCA do? First, in the covariance matrix, you subtract the mean, remember? So you're actually moving your origin to the center of that Gaussian distribution. And then PCA is going to give you the eigenvectors of maximum variance, meaning the directions in that space that maximize the variance of your Gaussian, right? So now you're actually going to rotate. Remember that we had this EI, the basis vector, and EJ, the second basis vector, right? And I'm going to rotate these to align my original basis vectors with my eigenvectors v1, v2, right? So I end up with a rotated space that represents my data like this. Actually, let me do this here. Right? So now the data is mean center, meaning I have subtracted the mean, right? Mean normalized. And I have rotated the space such as this dimension, the first dimension represents the dimension of maximum variance, the second one, the second maximum variance, and so on, right? That's what PCA does. Then this is called diagonalization, remember? Because now the covariance matrix in that new space, it's a diagonal matrix. Obviously, it's the diagonal matrix of the corresponding eigenvalues, right? Because the eigenvalues are proportional to the variance, right? And one step further I could do, I could normalize my data, capital X, where capital X is a matrix whose columns correspond to my samples, right? Then if I do this, then I obtain, actually, why don't we do this? Going to, well, call it Y, where Y is the projection of your data onto the PCA space, right? And then now I have whitened my data, which means that I have made this distribution equals to the identity matrix, right? And now my samples are going to be distributed like this, right? Right? Okay. And now here, remember, I can use the Euclidean norm, right, to compute the distance between two vectors, x1 and x2, or xi and xj, given the mean and the covariance matrix, right, that I have normalized. And that's going to give me the Euclidean distance because the mean has been subtracted, and therefore the mean is 0, right? And the covariance matrix is the identity matrix. So when I compute that distance in that mean normalized space, that whitened space, this is 0 and identity matrix. So I have now x minus mu. Well, actually, this is xi xj, xi xj transpose xi minus xj, right? And that obviously we call it the norm 2 of xi xj. And this is squared. You could copy the square root if you want of this and call it the 2 norm. All right. So that's one thing that we can do. Now, the problem that we have is that this is not always the case, right? Here we have made a huge assumption, which is that our data is normally distributed. It's a fine assumption because of the central limit theorem, right? This is actually a pretty good example, a pretty good assumption for our samples xi's, right? Because xi's are a combination of underlying hidden variables that we don't see called the latent variables, right? But what happens if my interest is in determining the latent variables, the hidden variables? This is pretty common, right? So instead of now being interested in x, I'm going to be interested in the latent variables, let's call them s. And I'm going to assume I have this linear model where A, it's a matrix that maps my latent variables into my observations, okay? Now, X, we said, X, it's a vector of p dimensions. Now, for the time being, I'm going to assume that S, which is, say, in q dimensions, is of the same dimensionality of X, right? Obviously, that's not always the case. We'll get back to that. And then A, it's obviously a matrix of P by Q, right? That maps from my latent space of Q dimensions, right? So my latent space, remember that word, or that these two words? The latent space of Q dimensions is mapped into the observation or feature space I observe of P dimensions, right? So that's what I have. Now, to solve this, I'm going to use another technique that we started talking about in our last lecture, which is called ICA, independent components analysis. And the reason for this is because I'm going to assume that my SIs are independent from each other, okay? And this I do basically inverting the idea of the central limit theorem. The central limit theorem says that if I combine simple or latent variables rather, S1 through Sm, right? And each of those are drawn from some underlying but unknown distribution, right? Once I combine them, I add them up together, right? The distribution of the combination, let's call it X, it's a Gaussian, right? So therefore, if my observation is Gaussian, then my latent variables are anything but Gaussian, right? Now, is it possible that my latent variables are Gaussian? Yeah, it is possible, right? I mean, in reality, everything is possible. However, given the number of possible distributions that there are in our feature space, or our latent space, which is an infinite number of them, by the way, right? The chances that that distribution is a Gaussian are very slim, right? It's not zero, but it's very slim, okay? So we can assume in general that my sources or latent variables SIs are non-Gaussian or non-Gaussian distributed. I'm going to assume that they are independent. So remember from the central limit theorem, IID, that was our assumption. That's the same assumption that I'm doing here. I'm also going to assume to derive ICA that my data, my observable data, is zero mean, and that the covariance matrix is the identity matrix, right? This is a very obvious assumption for us, and let's see why. So imagine that I'm here again in this case, right? And what I want to uncover are the latent variables. What are potential latent variables? Latent variables could be illumination. The illumination is going to have an effect on what I observe, but this is given to me, right? I have no idea what the illumination is. All I see is effects. I have no idea what the light source is with respect to the object and the camera, so I have no idea about the illumination. Pose. Pose is another latent variable. I have no idea what pose this image is taken in, right? Is this frontal view? Is it three-quarter view? Is the subject looking down, up, or what have you, right? I mean, we have no ways of knowing. So this is another latent variable. Is that a male or a female? Is that John or Anne? All these are latent variables, right? I have no idea. I cannot control them. They're not given to me, right? So all these latent variables affect my observation. Now, imagine that I want to obtain my latent variables. Let's say that I have two latent variables, right? So I mean R2 is R2 that I have drawn here. This is my feature space where I have my X, right? And I have two underlying latent variables. So X are drawn from this, and my S's are drawn also from this, which I'm going to call Q equal to 2, P equal to Q, okay? So R2 and R2. And my observations are these ones here. Okay, these are my observations. And the latent variables that I'm interested in are these ones. This is my first one. This is my first one, and this is my second one right here, okay? Okay, not working real well. Okay. Use this one. There we go. That's better. Okay. All right. So I have, they should go through the origin. So I have S1 here and S2 here. Okay. You see how this works? Now, let's see. Why not use PCA, right? I mean, I keep saying, I cannot solve this with PCA. Really? Let's find out, right? So maybe I could. So what I'm going to do, I'm going to compute the mean, right? So the mean is already at the origin. So the origin is not well drawn. So let me see. All right, that's better, okay? So the mean is already, the way I design it here, it's already at the origin. Now I'm going to compute the covariance matrix that looks like this, sigma x. So this sigma x, the way I've drawn it, it's already a diagonal matrix, you see? So all I can do, all I have left, is I can whiten the data, right? And what happens if I whiten this? Let's see. Let's check. So I have this space, and now I whiten. So this, I want to make it the identity matrix, right? So what's going to happen is that I'm going to end up with these points here. Like this, right? So my S1 is going to be here. My S2 is going to be here. Okay? And obviously my covariance matrix now is this one, which is equal to the identity, right? Yep. But have I recovered S1 and S2? No. I have recovered this one, V1, and V2, right? But these are not S1 and S2, right? If I recover V1, all I'm going to do, I'm going to project all these samples. You see these samples here? I'm going to project them orthographically onto V1, and all this orthographically onto V1. So V1 is going to have the information of both this source and that source. So they're going to be mixed by a matrix A, right? And V2 is going to have the orthographic projection of these ones. So it's going to be also a mix of this and this source. So I'm back in the original problem. I still have a mixing matrix A that is mixing both signals, right? But what I want is to recover S1 and S2, because if I did have S1 and S2, right, then these are already given solely by S1, right? All these ones would be projected onto a single point. So I know they are not from that source. And these other ones are going to be projected onto a single point orthographically onto S2. So I know they don't belong to S2, right? So that way I can separate them. But I'm almost there, right? PCA does not solve the problem, but it gets me really close. Once I've whitened the data, all I'm left is with a rotation, right? So I have this rotation from S1 to V1, which is the same as the one from S2 and V2, right? I'm left with that rotation, and not surprisingly, PCA is a Ricci transformation, and therefore it's given up to a rotation, right? Okay, so that's what ICA needs to do. It needs to find that rotation. If I can solve that rotation, then I find my sources. That's what I need to do. Okay, so how am I going to do that? Well, to get to this point, I have used the first and the second moments of my data, right? I have mean normalized my data, and I have whitened my data, right? So to get the rotation, I need higher moments. We said we're not going to use the moments, but we're going to use the cumulants, right? Because they are more convenient, mathematically convenient for us for the algorithms that we're going to be defining. And I told you that for the cumulants, all you need to know, I gave you the basic derivations of the cumulants from the moments, but basically all you need to know is a cumulant of order k is nothing else than the moment of order k minus some polynomial of the moments of order smaller than k. Okay? And we know that this is kappa. The cumulant of order 1 is 0. That of order 2 is equal to the mean, which is, or the covariance, which in our case, if it's normalized or whiten is 1. K3 usually is written as the third moment, and the fourth, which is the one we are interested in, is the fourth moment minus 3 times the second moment. Okay, squared. All right. Now the second moment, remember, is 1 because we've whitened our data, right? So therefore, this is, in fact, in our case, the fourth moment minus 3, right? Now, the fourth moment of a Gaussian is 3. So 3 minus 3, 0. So that cumulant is 0 for the Gaussian, right? So that moment, by the way, we called it the kurtosis, or kurt. The kurtosis of x, right? And what we want anything but Gaussian. So we want this kurtosis not to be 0. Okay? That's it. And what I need to show now is that this allows me to get the results that I want, meaning the sources. So let's see how that is possible. So I had here x equals as, which is obviously the same, right? You could also write s is equal to a inverse x, right? Same thing, right? You can go one way or the other. And I can do that because I'm assuming p is equal to q, right? In the general case, when p is different than q, things get a little bit more complicated than that. Okay. Now remember that I cannot recover my sources entirely, right? We discussed this in our last lecture, because the sources and the matrix A are defined up to a scale, because if I multiply by a scalar, let's call it lambda here, and I divide by that scalar here, then that's the same thing. And I can also multiply by the inverse of a permutation, A permutation times permutation S, right? So I do a permutation, and I also end up with the same thing. So let me therefore call this y. Y is just nothing else than some b times x, right? Where b is a vector of a matrix, let's call it capital B, right? That takes care of all these possible changes that I can have. And now let me substitute x here. So y is equal to b transpose x. It's equal to as. So I have as. And now I'm interested in the source, so I'm going to call this Q, vector Q, that is. So this is Q transpose S. Okay? That's what I have. Now remember that I want to show, rather, that the kurtosis of this variable, y, is going to allow me to find the sources. Okay? So let's compute this. This is the kurtosis of, let's see, this is kurtosis of Q transpose S, which is nothing else. I'm assuming I'm in two-dimensional space, so I'm just going to derive this for 2D. So this is the kurtosis of Q1 S1, right, times S1, plus the kurtosis of Q2 S2, right? And now I'm going to take Qi out, because that obviously is just the vector of numbers that I'm interested in, and then compute the kurtosis of S1. So this is the same as, this is going to be Q1 to the 4th times the kurtosis of S1 plus Q2 to the 4th times the kurtosis of S2, right? Now, what is the kurtosis of S1 and S2? Something different than 0, right? Because it's non-Gaussian. You agree? So, without loss of generality, let's assume that our kurtosis in our problem for Si it's equal to 1. So this is going to be equal to Q1 to the 4th plus Q2 to the 4th, right? Okay, so this is our result. What does this mean? That means that we need to compute the 4th norm of the vector Q, right? That defines the norm 4 of vector Q, right? So remember when we were talking about norms in our last lecture, that the Euclidean norm is nothing else than the circle. The 2 norm looks something like this. The 4th norm, excuse me. Okay. I could have drawn it worse, but much better too. Huh? Okay, so let me try again. Okay, I guess that's a little better. No, great. All right, you get the gist. Okay, so this is obviously Q1 to the 4th plus 2Q to the 4th, where this is Q1 and this is Q2, right? Okay. What else do we know? We have assumed that our data is 0 mean and unit variance. I can make the same assumption about my sources because they are defined up to a scale, right? So I can make the same assumption. So I'm going to make the assumption also that my sources are 0 mean and unit variance, which means that I have Q1 plus Q2. So I have the expected value of y square. It's equal to Q1 square plus Q2 square equals 1, right? Right? Okay. So what is Q1 square plus Q2 squared? That's a 2 norm, right? That's precisely the 2 norm. So let's draw the 2 norm here. The 2 norm is going to be a circle, isn't it? All right. It's going to be this circle right here. So I have, this is going to be Q1 squared plus Q2 squared. All right, and do I have solutions? I have 4 solutions, right? Here, 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 and here, right? These are points in my two norms that I get the exact same value, the exact same solution, right, for Q1, Q2. So for these four values of Q1 and Q2, I am making the two norm and the fourth norm equal to 1 or to whatever other scalar you want, right? Excellent. So let's write this down. My solution is for Q1 equal to plus or minus 1, right? Q1, which is symmetric, could be either 1 or negative 1. And the same thing here. So Q2 can also be plus minus 1. These are my four possible solutions. So let's go back to Q, what I have here, right? So if I use this, what am I going to get? Let's substitute Q for, let's do, so I have y1, y2, right? I'm redoing this, right? y1, y2 vector, right? This is my y vector. It's equal to Q1, Q2, right here, times S1, S2, right? Okay? And what am I going to get? Well, Q1, so let's say that I have 1, 0. I'm going to get y1 equals to S1, right? Excellent. That's exactly what I want to recover, right? I want my output to be one of the sources. If I have 0, 1, then I have y2 equals S2. Excellent. That's the other source I'm looking for. Or I could obtain them with negative 1 and negative 1 here, right? Which gives me the sources up to scale, right? Multiplied by negative 1. Fine. Great. So we just proved, right now, we just proved that if I maximize the kurtosis, or I equal the kurtosis to a scalar, and my expected value of y, excuse me, to that same scalar, right? That gives me an algorithm to find the sources. Right? So what's the goal? The goal is to find these points, right? Where for a fixed scale, let's say in S1, so this defines the sphere of one dimension, the circle, S1, so that in S1, I maximize the kurtosis, right? Now note I could make the kurtosis larger, right? By making Q1 to the 4 plus 2Q to the 4th larger or smaller, right? But then there's not going to be intersection with S1, so there's no solution, right? This is the maximum I can make that the fourth norm, the maximum I can make the kurtosis such that there is a solution, right? So that's my solution. So I want to maximize the kurtosis. And how am I going to do that? Well, we know that the maximum or the minimum of a function is given by the point where the derivative is equal to 0, right? So we're going to take that advantage, and we're going to define a criterion that allows us to do that. So I'm going to say W is my vector that I'm going to use to determine this. Now, W has to be a unit vector, right? Meaning W has to be on S1. You agree? If I'm in 2D or SP, or SP minus 1 in general, right? The sphere of P minus 1 dimensions, okay? All right, so we'll take the partial derivative of the kurtosis of my W, my Y, which is W transpose X, with regard to our parameter that I'm interested in, which is my vector W, which is the one that's going to give me my Q here. It's going to give me my sources, okay? All right, so I'm going to take the partial derivative of the kurtosis, and this is going to give me 4 times the sine 4 comes from the exponent 4 times the sine of W transpose X. This just returns either -1 or 1, whether the W vector is positive or negative. And then the expected value of, let's see, I have, what do I have? I have W transpose X to the 4th. So I take the 4th here. So I have W transpose X to the 3rd. Okay. Minus 3 times W squared. This is the 2 norm. I mean, if you want this, if you want to see where this comes from, this is nothing else than 3 times the expected value that I had, right, of W transpose X squared, which is nothing else than the 2 norm. So I'm going to substitute this by the 2 norm, okay? So 3 times W, the 2 norm. Now, the reason I'm not very worried about this is because this 2 norm, this just measures the length or the norm, right? The norm of my vector W, okay? Now, the norm of the vector W, I'm not interested in, right? This is a scalar again. I don't care about that. What I care about is the direction of that vector, right? Where that vector is pointing. So that vector like 1, 1 or 0, 1, and I'm sorry, 1, 1. 1, 1 or negative 1, 1, and so on. Okay. So what that means is that this is irrelevant. So I'm just going to keep that portion of my partial derivative. Okay. All right. So I want to optimize this. I need to start at something. So the way we're going to do this, I need to find the maximum. So I need to equal this to 0. And I need to find a way to make this 0. So what I'm going to do, because I don't know how to do it, I'm a little at a loss. So what I'm going to do, I'm going to start with an estimate of W, random estimate. So I'm just going to take W from SP minus 1, and I'm going to call this S0, okay? Now this 0 here means this is my initial estimate, okay? And for subsequent estimates, I'll say W of t, meaning the estimate at time t. Okay. So first, yeah. W is a vector in SP minus 1, right? Which is defined by this circle right here. In 2D, it's a circle. It's S1, right? So it's any vector here. Now, I don't know where the intersection of S1, which remember is my constraint right here, right? And my 4th norm, which is defining the kurtosis, I don't know where that intersection is going to be. It's going to depend on the problem, right? In this problem that we had here, this is where the intersection is going to occur, right? But I have no idea. That's what I'm looking for. I'm looking for that rotation. That vector W, it's going to give me that rotation, right? So that's what I'm looking for. I don't know what it is, so I'm just going to set it randomly at some point, right? I'm going to call this W0, and then I'm going to iterate this. So at each iteration, at iteration t or time t, I'm going to call it WT, okay? And now the algorithm is very simple. I'm going to do, this is the algorithm. I'm going to do an increment on W that is proportional, okay? It's some constant multiplied by this term that I have here. Now I'm going to take 4 out. That's another constant. I don't care. The sine, the sine of this thing, the kurtosis or W transpose X times the expected value of X W transpose X to the third. There you go. And then I'm going to do, so this is my increment, and now I'm going to do a time or interval or a step t plus 1. W is going to be equal to W at time t, right? So all this should be W at time t plus that increment or a constant that implement. And now I need one more step, because remember W is a vector on SP minus 1. So that means it has to have norm 1. So just to make sure that I did not go out of my sphere, I'm going to normalize this by its norm. That'll make it norm 1. I'll make sure that it stays in my SP minus 1. That's it, right? That's how I'm going to do that. Now there is a method that we saw in image processing that we can use. It's called Newton's method that iterates and allows you to do that. Let me review this for those of you that are not familiar with this very quickly. I'm just going to do a review. So that's going to, I'll keep this. All right. A quick review of Newton's method that we can apply to this problem and therefore find a solution for our sources. Remember, that's going to give me the direction of the vector in that space. That's going to give me the rotation that I'm looking for. So this is the algorithm. We already have the algorithm. This is it. There's nothing else. But to iterate this, you need an iterative method to find this. And what people usually use is Newton's method or an extension of Newton's. Now, of course, Newton himself did not define this method, right? I mean, I remember when I was a student that I kept hearing all these names, these 3-4 names, like Gauss, Newton, Euler, and so on. And I wondered, wow, these people were really good. How could they develop all these methods or all these theorems, right? You take calculus and algebra and all these names keep popping up. Like, obviously they did not. It just happens that someone derived these methods or these theorems or these results at a later stage, and because this method is going to use the derivative, they called it Newton's, right? Because Newton, along with Leibniz, designed or derived the derivative, right? Invented the derivative, just the basis of calculus. You might have also heard of a famous mathematician by the name of L'Hopital, a French mathematician, very famous, remember? I'm sure you have learned a lot about his theorems. Well, he just happened to be a very rich man, and he was interested in math. So what he did, he bought theorems from mathematicians and then published them under his name. That's why he's so famous. Yeah, it's funny. All right. So Newton's method. We'll start with a function f from Rp to Rp. So this is my function. This is a function of functions, obviously, of p functions. So f1 through fp. Okay. And we wish to find a vector. Let's call it, so this is our goal. we want to find a vector, let's call it x star, for which f of x star is the minimum, okay? The minimum of the function. Now, Newton's method uses the derivative and the known fact that the derivative has to be equal to 0. To derive Newton's method, we're going to need this following result from calculus that you may or may not remember. So let me refresh your memory. There's a result that you probably learned in calculus that says if I have a function fx plus some z, this is the same as f of x plus integrating from 0 to 1 the gradient of f of x plus as a constant vector z transpose z ds, which is nothing else than saying that I have f of x plus I integrate from x to z, right, in that interval, and the gradient of the function on, say, u du. Okay, so I'm going to use this final result here to derive the method. And what I'm going to say again, I'm going to use xt to refer to the value of x at time t. So if I have f of x at time t, and I want to add some value z to that f of x, then that's the same as f of x at time t, I should say, yes, at time t plus I integrate from x at time t plus my z, right, what I want to add, times the gradient of my function. Okay. Now, this is nothing else than the Jacobian, right? The Jacobian matrix. So what I'm going to do, I'm going to rewrite this as f, or this thing here, as f of x plus the Jacobian of x. Actually, why don't I say x at time t to stay consistent, time t times z, right? Excellent. Where the Jacobian is given by all the partial derivatives. So the Jacobian of f of x, it's equal to the partial derivative of f1. This is my functions that I have here. With regard to the x1, right? So x is my vector x1 through xp, all the way to the partial derivative of x1 with respect to xp. And then here it's the same thing, but for the different functions that I have, I said I have p or n, whatever it is, x1 and p. Okay. So I can put this together and define Newton's method. So Newton's method is going to be, let's see, I have my, remember, f of x star, this is the x star I'm looking for, plus the Jacobian of x transpose and z, which is how we want to deviate from here, has to be equal to 0. So I'm going to move this to the other side. So I'm going to It is t. I'm going to move this to the other side, so I have the Jacobian of x transpose is times z, excuse me, is equal to negative f of x transpose. And this is going to give me my z at time t. So now I can change x at time t plus 1 is going to be equal to x at time t plus z at time t. Okay? So I know my Jacobian, I know my function at time t, I can compute z, and I can add z to get my next estimate, right? And that's it. I keep iterating these 2 points, or these 2 steps, until I converge, and by convergence, we generally mean that that z value that we are adding into x is very small, smaller than some epsilon. Okay? Now, there is a famous theorem that says that if I keep repeating this for a convex function f, then that will find the optimal solution. There is also an extension of this, in which case you can go to the second derivative. If you want to go to the second derivative, then you compute the Hessian matrix. H, which is the matrix of second derivatives, right? And then the algorithm is the Hessian at time t times zt is equal to negative the Jacobian at time t, right? Same as this, but now with the first and second derivative here, and then the second step, which is the same thing, right? Doesn't change. All right, any questions thus far? So that gives us the first algorithm to compute ICA, right? It's really nice. Unfortunately, it doesn't work that well, but it's really nice. And the problem is that this function obviously is non-convex, and optimizing the function is not as easy as it sounds here. The function were convex, yes, that would be easy, but it's not. So other algorithms have been developed to try to address this. Another one, I'll probably sketch one, and then I'll talk about a more recent solution that's probably more interesting. So let's see. Okay. All right, let me sketch this solution only because we're not going to have time to do everything. All right. Another way to find the independent components, meaning that rotation that I'm looking for here, is to use entropy, neck entropy, instead of the moments. And that's slightly more robust, but it has problems of its own that we will discuss in a few seconds. So can I use neck entropy instead to find the basis vectors? So I'm going to define the entropy h of y. Okay, that's weird notation. That's not the Hessian. This is entropy. I don't know why I used the same. My bad. Okay. Anyways, the mutual information. I'm sorry. This is the mutual information, not the entropy. The mutual information is going to be equal to the log of f of y, which is precisely what I'm going to refer to as the neck entropy, which is equal to, let's see, I have a negative sign here, and then I integrate the log function of f of y, right? Differential of y. Okay, good. All right. Okay, so y here is my vector y1 through yp, and it's a random vector drawn from some distribution. Let's call it f. Okay? So f is the underlying distribution of y. And from here, I can compute the log of f, which is the expected value. It's the integration of this component. And with that, we are going to now compute how much this net entropy deviates from the another vector, or yeah, let's call it another vector z, I'm going to call it, okay, from another vector z, which is drawn from a Gaussian distribution, okay? So you have a vector that's drawn from a Gaussian distribution and a vector that's drawn from another underlying distribution, okay? So let's write this down. So I have a criterion J of y, which is my mutual information for z and y, and I want to compare them, and I want to make sure that the one for y deviates as much as possible from a Gaussian distribution. Okay. Okay, so the mutual information, let's call it y, is going to be equal to j of y minus the sum of all the i's of j of yi. And this is the net entropy of the function f of y projected onto the ith dimension given by my vector y. Okay, so y1 through yp. So I'm projecting everything onto the ith dimension. So I want to deviate from Gaussianity. I want non-Gaussian distribution. That's the same as maximizing the minimizing the mutual information. So what I'm going to do, I'm going to define this. I need to do that. I'm going to define this according to some moments of the data. So I'm going to compute the expected value of this function. Now, unfortunately, this function right here is given by this net entropy, okay, which is unknown to me because I don't have this f, right? I don't know what f is. So what I'm going to do instead, I'm going to come up with some function g of yi that approximates my underlying function f or n that I'm interested in. And I'm going to then rewrite this as the expected value of this minus the expected value of g for some other normally distributed variable. So here, this v, remember, is just drawn from a Gaussian distribution. Okay, so let's see how I can use this to derive a independent component analysis algorithm. So I have my source, my matrix A, no, wait, call it W here, A and X. A, it's equal to a matrix of, let's call it A1 transpose through AP transpose. And we have our Y's, which are equals to my AI transpose X. Okay. And now to derive an algorithm, all I'm going to do is I'm going to maximize the sum from 1 to p of my j function, but with respect to some g function that I have to come up with, of my vector, which I called AI, subject to, right? So I add the constraint under the constraint, or subject to, that the expected value of AI transpose X, AJ transpose X has to be equal to some delta IJ, some constant, doesn't matter. That's it, that's my algorithm, okay? Now, the problem here with this algorithm is that you need to come up with this function G that approximates the neck entropy, okay? And that's tricky. There's no single solution. It's very tricky. Some people have come up with functions that sort of work and give actually good results. And in that case, you can design a famous algorithm. It's called fast ICA that runs really fast and gives you the sources, okay? Still, in all these algorithms that we have defined up to now, we have that constraint. Remember that P is equal to Q, okay? And that obviously is something that we don't want, because if we have 10 people speaking at the same time in a room, that means I need 10 microphones, right? I mean, I'm going to be lucky I have 2 or 3 microphones, let alone 10. It's not going to happen. Okay, so let's see how we can solve this problem. And to do that, I'm going to define my last method. Or actually, I'm going to do 2 methods. Okay. I'm going to keep the same assumptions that I have here. My mean 0, my covariance matrix equal to the identity matrix. But this will not necessarily have to hold. And I'm going to present you 2 methods that are going to work really fast and give me the result that I want. And both of them are nothing else than an extension or a modification of the covariance matrix that I have used in PCA. So they can be seen as variants of the PCA algorithm. Okay. So the first one is very simple, very straightforward, easy to understand. So instead of computing, so again, this is for ICA, but instead of computing the covariance matrix, so PCA computes the covariance matrix, here I'm going to compute another matrix, so let me call it sigma rho, which is going to compute instead of the second moments, because this is nothing else than the second moments of the data, right? I'm going to compute higher moments of the data. So what I'm going to do, in particular, I'm going to compute the expected value of sigma I, okay, minus sigma I, and maybe I have some prior probabilities. We haven't introduced prior probabilities. I'm not going to talk about this. So I from 1 to C. Okay? And actually 1 to Q that it defines. Okay? So I'm going to compute for my group of samples that belong to some group. I'm going to compute the covariance matrix, and I'm going to compute the expected value of all the covariance matrices minus the covariance matrix, and that is an approximation of the fourth moment of my data. Okay? And then I'm just going to do PCA onto this matrix of fourth moments, and then my sources are either the eigenvectors Vi or are orthogonal to these eigenvectors. Okay? Now, how do I know whether it's the eigenvector is a source or is orthogonal to the source? Well, this is where my samples have to be. Remember, I actually erased the plot that I didn't want to erase. And remember that the sources have to be, they have to define the sample vectors, right? So if that source, if that eigenvector defines the samples, then that's a source. If the orthogonal vector defines the sources, then that's a solution. That's all there is to it. One problem with this method is that you need a large number of samples. Okay? All right, and now to our final method. Is that clear, this one? I mean, it's straightforward. It's just a simple modification of PCA. The final one I want to talk about is called Fourier PCA. It was only defined like 3 or 4 years ago, 4 years ago, I think, 2014. I posted the paper in Carmen, fantastic paper. It's one of the most impressive results in ICA that I've ever seen. And it has a good summary of everything that we've covered, of all the ICA methods. And it explains in detail the results that I'm going to summarize in a few minutes here, okay? Question? So again, we start with our matrix X. X is the samples x1 through xn, right? Our n samples. Each xi, I'm going to assume, is defined in p dimensions. Our sources, SIs, are defined in q dimensions. And here, in that approach, you can assume that at most one source, right, let's call it maybe Sj, is drawn from a Gaussian distribution, say of zero mean and identity matrix, right? For at most 1j, okay? Just one. All right. Obviously, we have x equal as with a rotation matrix from p to q, or from q to p, rather. I'm going to start with the assumption that p is equal to q and then generalize it, which means that the rank, or rather than a, its full rank. Okay. So what I want to find is my columns. Let me call the columns A1 through AP. Okay. So these are the columns, or AQ if q is different than p, but for now, you can assume actually, because I've already said, why don't I say q? Okay. And now what I'm going to do is I'm going to use a trick to find the rotation of my basis. So remember what I have. I have my space, right, that I have whitened already. So my samples look like this. My covariance matrix is already the identity. And now what I'm looking for is the rotation between my eigenvectors of the covariance matrix, right, and the the independent components S1, S2 of my sources, right? So I'm looking for this rotation. Now this rotation is in the complex domain is written as, so if this is I and the imaginary axis and this is the real axis, it's nothing else than some exponential e to the power of some rotation, right? Okay. So I'm going to actually use this fact. That's what I'm trying to find. I'm trying to find a rotation. And to do that, I'm going to use the Fourier basis to do that. Okay? That's why they called it Fourier PCA. And it has many applications, this algorithm, not only for ICA, but pretty cool. So let's see how we can do that. Now, we're going to start with the characteristic function. Remember, we've already talked and used the characteristic function, which we defined as phi of omega, which is equal to the expected value of the exponential function j omega x. Now this j, remember, is the complex number, right? Square root of -1. It's more convenient when you work with exponential functions to work with the log. So you will see this quite often, that instead of this, you may work with phi of the log of this. And we're going to assume that the cumulant of k order, and this is really cool about this method, the cumulant doesn't have to be the cumulant of order 4, can be any cumulant, okay? But k has to be larger than 2, because remember, the cumulants of order 1 and 2 are non-zero for all the distributions, including the Gaussian, right? But we're looking for non-Gaussian distributions, right? So the cumulant of some order larger than 2 has to be non-zero, okay? So it has to be larger than 0 for some k larger than 2. Okay, so to do that, what I'm going to do, I'm going to take I'm going to compute the derivative, the first derivative of the log of my characteristic function, okay? So let's see, if I take the derivative with respect to u, obviously, of this, I'm going to get, so this, the log gets rid of the exponential function, and I'm going to do that with respect to u or w. So I'm going to get, let's see, this is the expected value of j x e to the power of j u transpose x over phi of u. This is just a normalizing factor. And I can compute also the second derivative, which is the expected value of I x e j u transpose x phi of u. And again, u is just here drawn from a normal distribution. any point, doesn't matter. Okay? Just drawing from a normal distribution, that's going to give me that vector that defines the rotation that I'm interested in, right? Right? So the same saying as SP minus 1, right? Okay? Yeah? This is the vector of the rotation I'm looking for, right? Okay. Now let's look at this expression that I obtained here. This expression, oops, actually, I forgot some terms here, didn't I? Okay, I did the first part and I forgot the second part. The second part is, that's the same thing. And then this is EJ X JU transpose X squared. There we go. That looks better. Okay. So, what's this? We've already seen this. What's this? The second derivative, the Hessian, right? Right? That's a Hessian, right? The second derivative. Okay. So we have that. And we're going to note now that I can rewrite this second derivative as A. Remember, A, it's our matrix that we're interested in, right? That's what we really want to recover, times a diagonal matrix of something and A transpose, right? And what's that something? That's the second derivative precisely that we have computed here. So the second derivative of our characteristic function, AU transpose U I, right? I should be sub I, right? Meaning the ith entry of that column, but once projected onto U. Okay, so this is the diagonal, so this is equal to this, right? That we have derived here. Perfect. So what that means now is that I can compute a covariance matrix of U, of my vector U that I'm interested in, which is nothing else than the actual covariance matrix, but with a multiplier, which is this multiplier here that I have used, or this multiplier here, right? This thing here, right? So you see, this is A transpose, which is nothing else like covariance matrix, but with this multiplier. So let me write this multiplier right here. This is from 1 through n e to the power of, this is right here, j u transpose x I the sample, the ith sample, I have n samples, divided by, I'm just going to normalize this with all the weights that I have. Let's call this j, or actually I have used j for the complex number. Let me use k, 1 through n of xi minus mu u, xi minus mu u transpose. That's it. Where obviously mu u is the mean of the vector u, so it's the weighted mean, right? So it's 1 over n, the sum from 1 through n of xi times the weight, weight I, where weight I is this thing here, right? So this is weight I. So what's this? This is nothing else than a weighted covariance matrix, right? That is weighted by these exponential functions that are going to define the rotation that I'm interested in, right? So it's simple. And these exponents you can show are the same as the Fourier exponents, right? That's why they call it the Fourier PCA. So we're just doing PCA now on that new covariance matrix of these vectors that define the rotation, right? It's absolutely awesome. So let's. U, it's our vector. I have written it down here somewhere. Give me one see where. I wrote it down somewhere. U is our vector that is drawn from a normal distribution, right? U is a vector, right? This is a vector U right here, right? This vector is the vector that is going to determine my rotation, right? So because I have, this is the identity matrix, so that defines SP minus 1, right? Or the same, that's the same as saying that I have a normal distribution with mean 0 and identity matrix, right? These two things are equivalent. And that means I need a U that's drawn from here, right? That gives me this rotation, right? That gives me this direction that I'm looking for, the rotation of the space, right? Because PCA is able to get me this far up to a rotation. And I'm looking for that rotation. And that vector U tells me what that rotation is, right? So I just put that vector U here. And then what this does, it computes with the samples that I have, the covariance matrix with respect to our parameter U that we're interested in. And now all I need to do is to do PCA on that sigma U, right? And what I'm going to obtain, I'm going to obtain my eigenvectors, V, right? V1 through VQ, that these columns are going to be my sources, okay? So these are going to be my sources. Now, there's one step that I did before I applied all this, right? Before I did all this, I had to whiten my data X, right? So that means that before I say that these are my sources, now I need to map them back into the original space. So I need to do the inverse of the whitening transformation, right? But basically, after that, these are my sources. That's it. Because this is precisely a PCA on the vector U that defines the rotation I'm looking for. This is the coolest part of this algorithm. All right, I'm out of time. I'll finish the details of this algorithm, and I'll tell you a couple of extensions of how to make P not necessarily equal to Q, and how to make it run rapid or fast in a computer, okay? All right, I'll see you next week.